Rust does not handle errors like many other languages, and that is exactly why beginners often get stuck. In this video, we will walk through 14 practical error handling examples using result, option, match, and the question mark operator. No long theory, just real code patterns you can use immediately. We start with the option type because many Rust error handling habits begin with handling missing values clearly. These examples show how to deal with data that may or may not exist. Imagine we are reading a username from a user ID and that ID may not exist. We write find user so it returns option string. Then we use match to handle some and none separately. Now we run it and look at the two different paths. Let's break down the result. The first lookup returns sum, so the name is available inside that branch. The second lookup returns none, and Rust makes us write what should happen there instead of pretending the value exists. Now let's show the best habit for this pattern. Use match when both outcomes deserve meaningful logic. It keeps the code honest and makes missing data a normal branch, not a surprise crash. For configuration values like page size, a missing value often just means we should use a default. Here we parse an optional string into a number, then use unwrap or 20 when no valid value exists. Now we run the code and compare the configured case with the missing case. Let's break down why the output is different. When the option contains a valid value, unwrap or leaves it alone. When the option is none, it substitutes the fallback value immediately. Now let's show the best use case. Unwrap or is great when the fallback is already cheap to create. For expensive defaults, we will use a lazy version in the next example. A default cache directory might allocate a string, log a message, or read configuration. We put that work inside default cache dir and pass it to unwrap or else, so it only runs when the option is missing. Now we run it and watch when the fallback message appears. Let's break down the output. The first line appears without the fallback log, because the value already exists. The fallback log appears only before the second result, where the option is none. Now let's show the better rule of thumb. If the fallback does real work, make it lazy with unwrap or else. That keeps the fast path clean and avoids hidden extra computation. Next, we move from checking option values to transforming them. These patterns keep code compact while still preserving the missing value case. A profile screen might receive an optional username and still need a display label. We use map to turn a real username into a handle, then unwrap or to show anonymous when there is no name. Now we run it and check both cases. Let's break down why this stays so small. Map only touches the value inside sum, so we do not need to manually match just to format a string. None passes through unchanged until the fallback turns it into anonymous. Now let's show the best place to use map. Keep it for clear, single-step transformations. If you start adding complex branching inside the closure, switch back to match. In a real app, getting an email might mean finding a user, then finding a profile, then reading the email. Each step can be missing, so we chain them with and then instead of nesting 3 matches. Now we run it and compare a complete profile with an incomplete one. Let's break down the chain. If find user returns none, the next lookup never runs. If the profile exists but the email is none, the final result is still none and the match prints the missing email message. Now let's show the best rule for this pattern. Use and then when the next operation can also fail with none. It keeps the happy path readable while still preserving every missing data case. Now we move between option and result. This is common when missing data needs to become a real application error. In real services, an API key might start as an option because it comes from config or the environment. But before sending a request, missing data should become a descriptive error. We write require API key with OK or else, use question mark and send request, and now we run it with one key and one missing value. Let's break down why this works. Sum becomes OK, so the request continues normally. None becomes with our message, and the question mark returns that error before the request body run. Now the best practice is to prefer OK or else's when the error needs to be built. It avoids creating the string on the success path, which keeps the common path clean and cheap. Next, we handle result directly. Matching is the clearest starting point when both success and failure need visible behavior. Configuration values usually arrive as strings, but the app needs a real number. We parse each string as a US16 and match the result explicitly. Now we run it and compare a valid port with bad input. Let's break down the result. The string A to the 80 becomes OK. so we get the port value. The string ABC cannot be parsed as a number, so Rust gives us an error, and our error branch turns it into a readable message. The best practice here is to use match when the error branch has real behavior. If you need to log, recover, explain the problem to a user, or choose another path, explicit matching is often the most readable option. Now we use propagation. This keeps the successful path readable while still returning real errors to the caller. A timeout value often comes from a file, and both reading and parsing can fail. We write load timeout so it returns result. Then use question mark after each fallible operation. Now we run it with a valid file, a missing file, and an invalid file. Let's break down the flow. For the valid file, both operations return OK, and we reach the final OK timeout. For the missing and invalid files, the first failing question mark returns early, so the caller decides how to print the error. The best practice is to use question mark when the current function cannot fix the error. It keeps the main path easy to scan and still gives the caller a real result instead of crashing the program. Next, we transform errors. The goal is to make low-level failures useful at the application level. When a form has many numeric fields, a plain parse error is too vague. Here we parse a customer ID and use map error to attach the field name and original input. Now we run both a valid ID and a bad value. Let's break down why this result is useful. The valid input is still just the number 42. Only the failing input goes through map error, where we turn a low-level parse error into a message that says exactly which field failed. The best practice is to add context right next to the operation that can fail. At that point, you still know the field name and original input, so the caller does not receive a vague parse failure. Finally, we recover from an expected failure. A fallback is still fallible, so it should stay inside result. Apps often prefer local configuration, but they can fall back to defaults when the local file is missing. We try to read config to local toml first, then use or ls to read config to local toml only after a failure. Now we run it with no local file and a default file present. Let's break down the recovery. The local read returns error, so or else runs the fallback closure. The default read returns OK, so the final result is successful and tells us which config source was loaded. The best practice is to use or else only for intentional recovery. Make the fallback visible in the output or logs, because silently switching configuration sources can make production issues hard to understand. Now we move into batch-style error handling. These patterns matter when one piece of data becomes many items, and your code must decide whether to fail fast or keep the usable values. When you parse a batch of product IDs, one bad ID can make the whole import unsafe. Here, we map each string into a parse result, then collect the iterator into one result containing a vector. Now we run the program and compare a fully valid batch with a batch that contains one bad ID. Let's break down why this works. The map step creates an iterator of result values, not plain numbers. Collect understands that shape, so it builds a vec only when every parse succeeds, and otherwise returns the first parse error immediately. Now we show the best default for all or nothing batches. Use this pattern when a single bad item should reject the whole operation, like importing IDs, reading required config rows, or validating payment records. It keeps the control flow short and makes the failure rule obvious. Sometimes invalid values are not fatal. For optional numeric tags from user CSV data, partial success can be the right product behavior. We parse each tag, convert successful parses into option values, and now we run it to see that only real numbers remain. Let's break down the important part. Parse gives us result because parsing can fail. Calling OK removes the error details, and filter map keeps only the successful numbers, so bad and empty values simply disappear. Now we show the safer rule for this pattern. Filter map is clean, but it hides errors, so use it only when skipped values are expected and acceptable. If the user needs feedback, collect results or store the rejected rows separately. The last section is about application-level errors. Instead of passing around raw I/O and parse failures everywhere, we model the failures our program actually cares about. Real applications often need to know what kind of failure happened. Loading an account balance can fail because the file is missing or because the file contains bad data. We model both cases in app error, then run 3 scenarios: valid input, missing file, and invalid contents. Let's break down the conversion. Read to string returns an I/O error, and parse returns a parse error. because app error implements from for both of them. The question mark operator can convert each failure into our application error type. Now we show when this is the right design. Use a custom error enum when other code needs to react differently to different failures, like retrying I/O but rejecting bad data. Typed errors make those decisions explicit instead of relying on string messages. The manual enum works, but production code can get noisy fast. With this error, we keep typed errors and remove most of the boilerplate. We define a CLI error type, run valid and failing cases, and now we check the clean messages in the terminal. Let's break down what this error is doing. The error attributes become the human-readable display messages. The from attributes generate the same conversions we wrote manually in the previous example, so the question mark operator still works. Now we show the production rule. Use this error when your library or internal application code benefits from named matchable error variants. For a top-level binary where you only print the error and exit anyhow can be simpler. But this error is better when exact error types matter. Now you have 14 practical Rust patterns for handling errors without relying on panic-driven code. If this helped, subscribe, like the video, and write in the comments which Rust topic or real-world example set you want next.